everybody, welcome to 3 Ways to Improve Your Regression, Part 2. We're going to get started now. Thank you for joining us. My name is Caitlin Onthank. I'm a marketing statistician here at Salford Systems. And for those of you who don't know us, Salford Systems is a data mining and predictive analytics software company. So if you are registered for this webinar, you'll be receiving a follow-up email to the address that you registered with, either today or tomorrow. And this email will have a recording of the webinar, the slides that I'll be using today, the data set that I'll be demoing, a tutorial on how to replicate the steps that I'll show you, as well as download instructions for the 30-day free trial of the software I'll be showing you today. So here I have a little outline of what we'll be going over today. First, I'm going to start with a quick review of Part 1. Now, if you missed Part 1, you can still register to review the recording on our website. So I'll quickly go over the concepts we covered last week, as well as the results that we saw. Then I'm going to go a little more in depth on 2 of the methods that you saw last week, nonlinear regression splines and stochastic gradient boosting. With the regression splines, we'll look into reading the basis function code that you get from the model. We'll look at some of the plots that the model produces, and we'll also look into including interactions, since we didn't do that last week. For gradient boosting, we'll look at interaction control, the partial dependency plots that we touched on briefly last week, and how to do spline approximation to these plots. Finally, we'll look at some case studies and other applications based on the feedback that I got from last week's webinar. Now, we are covering a lot of material today, so I'm not sure if we'll be able to get to questions. I'll get to some if I can, and anything else that remains I'll answer by email as I did last week. Okay, so recap of Part 1. The first thing we did was we talked about ordinary least squares regression, or OLS. We talked about some of the common issues that you can come across in your data that OLS doesn't always handle well, including missing values, nonlinearities, interactions, how to select your variables, the problem of overfitting, and the problem of collinearity. And as a solution to these problems, I introduced 3 different methods: nonlinear regression splines, stochastic gradient boosting, and random forests. So I showed you these in the software, as well as talked about some of the theory behind these methods and the advantages of each. Now, these are common methods in data mining and predictive analytics. So the ones I'll be showing you today in the software, we call Mars and TreeNet for the top 2. This is just our license name for these algorithms, but they are widely used in the data mining world in other ways. To illustrate the methods, I showed you a concrete strength prediction problem. So we had about 8 or so predictors that were components of concrete, such as cement or water or the age of concrete, and we tried to predict the strength. We used 4 of the methods: OLS, Mars, TreeNet, and random forest. So this table just summarizes what we saw in terms of mean squared error and R squared. And it's pretty obvious that we were able to improve accuracy greatly using the 3 different methods. Now, the feedback that I got from Part 1, I promise you I read through everything that you had to say, and I'm trying to incorporate that in this week's webinar. There were many different suggestions, and we'll also attempt to gear future webinars to what you guys have provided as feedback for what you would like to see. Okay, so the first topic here is nonlinear regression splines. So this is what I went over last week. I'll explain it quickly again, and then I'm going to switch to the software to get into more of the advanced features. So a simple illustration of an XY relationship from these 2 pictures at the bottom. On the left, you see a standard OLS solution. You have your data points, which are the red dots here, between an X variable and a Y variable. And OLS simply fits this black line straight through the data. And as you can see, it doesn't do a great job. There's a little bit of underestimation on the far left and on the far right. So instead, we want to use regression splines to better approximate the data. And the way we do this is we find knots in the data region. And so the picture on the left points out these knots with arrows. So we have a knot here, it looks around 4, maybe another knot around 8, and another knot around 22. So after the algorithm finds these knots, regression splines are fit in between each of these knots, and we call these basis functions. And these basis functions decompose the information in each individual variable. And this is what we call MARS, multivariate adaptive regression splines. So it's similar in nature to just a set of OLS models. And it allows for bends and changes that are seen in your data. And as you can see, this black line on the right fits the data much better than the OLS solution on the left. So now I'll switch to the software. And I'm going to start by quickly building the same model that I showed you last week, so then we can build upon that model. Now for those of you that didn't watch last week, this is our Salford Predictive Modeler, we call SPM. This is the GUI version. We also have a non-GUI version, and this is what I'll be using today just to illustrate these methods to you. So I need to open up our data set. I'll import this concrete Excel file, and this is the same one you'll be provided in the follow-up email. When I click Open, we see a window that tells us how many records are in the data. We have a little over 1,000 records. And we also see a list of our variables to the left. Strength will be our target variable that we're trying to predict with these other components of concrete. Okay, so I'm going to get straight to modeling here. When I click button, we have a model setup window. And in the bottom right is where you can choose which engine you'd like to use. So last week I showed you regression first, and then I moved to Mars regression spline. So we'll jump right into Mars. Our target type is regression, and our target variable is strength. And we'll use all of the remaining variables as predictors. As I mentioned last week, we also want to have a test sample. Since this is a fairly small data set with only 1,000 records, I'll be choosing 10-fold cross-validation. And what this means is that you separate your data set into 10 different parts. You use 9 of those parts to build the model and the 10th part to test the model. And then you repeat this process 10 times, leaving out each part once, and then combining the model performances. So this is a widely used testing method, and we'll be using that today for both our regression splines and our gradient boosting. The last thing we want to change in our model setup is on the Mars tab. As I mentioned before, basis functions are the regression splines that decompose each variable. So because we have 8 predictors in our model, we want to increase this number to allow for more nonlinearities within each variable. So I'll change this to 40. And also note that we're keeping our maximum interactions at 1. So this is a strictly additive model. And later on I'll be showing you what happens when we increase this number to 2. But for now, we'll just rebuild this model that we saw last week, and I'll click Start. So in our Mars results window, we get a graph of the number of basis functions against the test criteria. We can change this to mean squared error since that's what we'll be working with. So what happens is the algorithm adds basis functions one at a time until it reaches the number that the user specified, which in this case I specified 40 basis functions. And I got several questions about this last week, which is why I'm going over it now. So why do you only see 28 here? What happens is when you add 40 basis functions to your model, sometimes these basis functions can be linearly dependent on each other. So the algorithm automatically discards these redundant basis functions to avoid the problem of collinearity. So in this case, we only ended up with 28 basis functions. What happens after this is a backwards elimination stage to produce this sequence of candidate models. And then these models are tested on our test sample. In this case, we used cross-validation. Now that we have a test performance for each model, you can click throughout the sequence if you like, but the optimal model is denoted by this green bar here. So now we can see some statistics about this model by clicking the summary button. This is where you'll find your mean squared error on both the learn and the test sample, as well as your R squared. So we're getting the about 88% R squared that we saw last week. So I pretty much stopped here last week just to give you a flavor of the regression splines, but I want to take it a little further and show you some of the more detailed reports that you can get from Mars. I believe I mentioned variable importance. This is always the first tab I look at because you want to know which variables are contributing in your model right off the bat. It's a quick way to do it. We can see age and cement are the most important. The next tab I want to look at is basis functions, where you see the code for your model. I had a couple questions about how a regression spline model is more complicated than an OLS model. So this is where I'll explain that. So for each basis function in your model, there will be a line of code here. This is the proof that 40 basis functions were created because you can see that we do have basis function 39 in this model. So that wasn't discarded. Basis functions always have the same form of max of 0 and an expression that includes one of the original predictors. Now this might look a little confusing, so I will explain with the plots in a few minutes to show you how these are constructed. But the gist of it here is that each basis function gets its own line of code. And then at the bottom, you have your nonlinear regression equation, which looks very similar to a standard regression equation. You have your y equals, you have an intercept term, and then you have your coefficients and your basis functions. So you can view this either in SAS, which is what you see now, or in BASIC, which is SPM's built-in. So even though this is a little bit more complicated than a standard regression equation, it's still fairly small in terms of code. In this model, 28 basis functions. So you'll have 28 lines of code here. If you have a model that only has 5 or 6 basis functions, you'll have a much simpler of code. Now, how do these basis functions work? To illustrate this, I want to move to the Plots tab and show you the plots that are produced by the Mars model. Now remember, I am not including interactions in this model yet, so we have strictly additive models, so only 2D plots are created for each variable. Show all the basis functions plotted for each of the individual variables in our model. Now to better explain this, I'll go back to basis and show you how this works. So each basis function incorporates one of the original predictors. Basis function 1 is the max of 0 and age minus 56. So this number here, which we call C, or R naught, occurs at 56 in this age plot. So you can see here that there is a change in splines. And so these basis functions incorporate these different knots and different slopes based on your final regression. So the next set of basis functions we can see for cement happens at knot 531. You look over here, you can see, in fact, there is a slight change. And I'll open this so you can see a little bit closer. So all this is doing is letting you know where the changes are happening in each variable. So it's really simple once you grasp the concept of a function is showing you and how they're combined together in a full equation. So why does Mars by default only give you an additive model? Now what can happen is once you start adding interactions into your model, it can become quite complex. So that's what I'll show you next. I'll show you how the basis functions and the plots change when you include interactions in your model. So I will go back to model setup. We have a shortcut here. We'll keep everything the same here in our model tab. Same predictors, same target variable. I'll go back to the Mars tab here and I'll change maximum interactions to 2. So now we're saying that we're allowing two-way interactions among all of the variables in our model. And because we're adding more complexity, I'm going to increase the basis functions to 50. And these are numbers that you can play with based on your data and based on the results you see. You might decide to increase your basis functions. Now what happens when you increase maximum interactions to 2 is you're allowing two-way interactions among all of your variables. If there are certain variables that you don't want to be interacting in the model, you can control that on your model tab. As you can see, there's a column to the far right here that you can check variables as non-interacting. So if I didn't want age to interact in the model, I could check that here. Additionally, if there are certain pairwise interactions that you don't want to appear in the model, you can denote that on this Interactions tab. Now this tab becomes active once you've set those maximum interactions to 2. So in here, if you didn't want age and cement to interact, you would just simply uncheck this box. So you have a pretty fine control over which interactions will be in your model. I'm just going to leave the defaults and let everything interact as is. Start. Okay, so we have our size model. We can already start measures on the test performance, and our MSE have improved from the model with no interactions. Just a slight improvement. But now you can see that we have 48 basis functions. So we're already almost doubling the complexity of our model by including more interactions and basis functions. To see that in action, again, click the Summary button, and we'll go to the Basis Functions tab. We can see we have limits for this model. The other difference is we're now seeing cross products in our basis functions. So for example, basis function 11, you see your typical statement, max of 0, but now we're multiplying by basis function 10. So this is where the interactions are coming into play. So as you can see, this engagement minus 14 increases the complexity of your model. So you are getting a little bit more accuracy, but you're sacrificing simplicity. Additionally, you'll see this change in the plots. When I click the Plots tab, we're now seeing 3D surfaces only. And when I click these, you'll see some complex plots. So keep in mind, if you do want to include interactions in your model, you are going to be looking at a different output. So this is something you have to decide if you would like a simpler model with a little bit lower accuracy, or if you'd like to squeeze out all the accuracy you can at the cost of interpreting 3D plots such as this. Now, again, you can control your interactions, so if you decide to only keep the age and water interaction and keep everything else additive, you will get the 2D plots for all of the additive variables, as well as this one 3D plot. So there's always a little give and take depending on what exactly you're looking for and how your data is behaving. Okay, so I decided to show you this first just so you could see it kind of as a sequence. And now I'll switch back to the slides and go a little bit more in depth on what I just showed you. And hopefully it'll make sense better this way. I included this slide again because I did have a lot of questions last week about the modeling process for Mars. As I explained from the results window, it starts with a forward stage. It adds pairs of basis functions at the same knot in a stepwise regression manner. And this process only stops once they've reached that upper limit. So in this case, when we reached 40 basis functions. And then any redundant basis functions are discarded. And this is automatic because of linear dependency. And this is the reason that Mars is resistant to multilinearity. So that's one of the solutions to the OLS problem. After all of the basis functions have been added, there is a backward stage that removes the basis functions one at a time, again in a stepwise regression manner. And this creates that sequence of models that we see in the Mars results window. Again, they're varying complexity. You could pick a smaller model with only a few basis functions, or you can pick the model with the most basis functions. Finally, there's a selection stage. We let you know what we think is the optimal model based on the test performance, and this is the modern approach. You'll also notice that it gives you the GCV criterion, and this is a legacy approach that we have in the software for those that still may use it, but we do recommend using the test performance. The next topic that I showed you in Mars was the basis functions code. Now again, these basis functions are used to express the knots. There are two different types, direct and mirror, and this simply means which way the basis function will be jetting off of that knot. So the direct, it will go to the right, and the mirror will go to the left. And these are the basis functions that you saw in that tab in Mars. And all it is a continuous transformation of your variable, your original variable x into a new variable x star. And that value of c just defines your knot placement. So here I just took an excerpt of that model to show you 5 simple basis functions and how they're set up. So basis function 1 is a direct basis function. Basis function 2 is the mirror of that same basis function. So they're always added in pairs. And if there's any linear dependency, one of them will be eliminated. The next thing I talked about was plotting these basis functions. Here is the water and the age plot from the cement problem. And there are clear nonlinearities, especially in this water plot. And I also included the 3D plot. Now, if you're like me, these 3D plots aren't easy to read, and so we also have the option of looking at it more in a heat map. It's a little bit easier to read. As I mentioned, purely additive models will produce 2D plots for each predictor, and models with interaction effects will be producing these 3D plots. So again, it's up to you and the type of output you're looking for. Finally, we talked about interactions. So last week we only incorporated nonlinearities because that's the default here. And this week I talked about including interactions as well. So it increases the complexity, but we did see a higher accuracy. So what happens with including interactions in Mars? First, Mars identifies a candidate pair of basis functions, which I mentioned before were the direct and the mirror basis functions. What happens next is the contribution is tested when this pair of basis functions is added to the model as standalone. Next, this pair of basis functions is tested when interacted with basis functions that are already in the model. So the interactions are built by accretion. Now another main difference is a Mars interaction is region-specific. So it's not like a typical interaction that you'd see in an OLS equation where it's just variable x1 times variable x2. Because Mars is operating on separate data regions. So instead, you'll be getting interactions that, for example here, these two variables pt and rm. So this isn't just the interaction of pt times rm. We're multiplying pt greater than 18.6 and rm greater than 6.431. So it's a little bit different. And it also allows Mars to construct different interactions between these two variables outside of this region. Now this can get a bit complicated, and you might be wondering, well, which model should I be using? And so we do try and help you out here with model automation. We recommend that you try an additive model as well as a model with two-way interactions and possibly three- and four-way interactions as well. Depends on the data and how interactions are present in your data. So at the end of this, I'll be showing you some model automation, and I can point out how you can run your Mars model automatically with each of these different settings. And then you can view them side by side to see which one works best. So we're about halfway through the webinar now. I understand this is a lot of material and I might be going a little bit quickly for you, but I want to make sure that I touch on everything that we promised and also touching on some of the feedback that I received last week. So this is everything on Mars. Again, if you have any questions, there is a question pane on the webinar, and feel free to type those in. I'll get to them at the end if I can, or offline later today. So now we'll be moving on to talking about stochastic gradient boosting. This is another solution to some of the problems we see in a standard linear regression, and this handles it in a little bit of a different way than Mars. Mars is nonlinear regression splines, and we're still seeing that regression-like equation at the end. Gradient boosting is a little different because we're actually using small decision trees. So for those of you who don't know how a decision tree works, I'll explain that quickly. In the bottom left here, we have tree 1. Now what happens is you have all of your data in this top green square here, which we call a node. What the algorithm does is it looks for the best way to split this data into two separate subregions. So for example, if you have a group of 100 people, you might decide to separate them based on their age. Everyone older than 50 goes into one subregion, everyone younger than 50 goes into the other. The algorithm keeps on splitting the data in this way. It's a data partitioning to reach these final subgroups that tell you something about your data. So this is a very small decision tree, and what stochastic gradient boosting does is it combines many of these trees together in an error-correcting sequence. So tree 2 will try and predict the residuals from tree 1. You're essentially just trying to correct the mistakes you made in the previous model. And once you add them all together, you have an extremely accurate model. Here I'm only showing 3 trees, but we usually build a minimum of 200. It's extremely fast and efficient. It's completely data-driven, which means we're not operating on any distributional assumptions. We're just looking at the data and trying to find the patterns. So there are many advantages to using gradient boosting, and we'll be taking a step further today to show you how gradient boosting can produce extremely insightful plots and how you can put approximations to these plots to create transformed predictors if you want to use them in a standard regression setting. So now I'll switch back to the software. We'll run through some of the gradient boosting features, and then I'll come back and explain them in the slides as I did with Mars. Okay, so I'll open up Model Setup again, and I'll switch the analysis engine to TreeNet gradient boosting. Everything stays the same here. We still have the same target variable strength in our predictors, and we'll be running a regression. When I click the testing tab, we'll see that we're still doing tenfold cross-validation. Another thing I'll change here is in the TreeNet tab, I'm going to increase the number of trees. So as I mentioned, we build a minimum of 200 trees. I'll change this to 500, just so we can see a bigger model. There are many other different parameters you can change here if you're more advanced or if you've used gradient boosting before. You'll see some familiar things such as learn rate or loss function. If there's a specific loss function you'd like to optimize, you can choose that here. Finally, the last thing I'll do is talk about this TreeNet Interactions tab. We talked about interactions with Mars, so we'll be talking about them again with TreeNet. And unlike Mars, TreeNet automatically includes interactions. Every time you partition your data set more than once, you're automatically introducing interactions because you're using a different variable after you've already split with another variable. So with TreeNet, you have your interaction control language, and this allows you to denote how you want interactions to play a part in your model. So by default, all variables will interact. You can also choose that no variables interact and have a strictly additive model, or you can choose which variables you'd like to interact. So for example, I could put age over here and cement over here. And that would restrict only these two variables to interact with each other, and everything else would be additive. But for now, we'll leave it on the default. I came to this tab because I want to select a reporting feature. I'll check the box next to General Interaction Strength Reports. What this will do, this will give us some output to detect which interactions are the strongest in our model. Now I'll click Start. So we're building 500 decision trees here. As you can see, it goes fairly quickly considering the computation behind it. The great thing about our new SPM as well is cross-validation folds are done in parallel, so that goes extremely quickly as well. So our TreeNet output looks different. We see a graph of the number of trees in the model against the mean squared error. Now I only built 500 trees here, and that's saying that's our optimal model. And this means that we might not have learned as much as we possibly could have. So in this case, you'd want to increase the number of trees here. Now, I ran some experiments on this data set earlier, and I was growing up to 10 to 15,000 trees to reach the best R squared, which was around 95%. So I don't want to waste time doing that in the webinar today. You're welcome to do that on your own time if you'd like. Okay. What we'll be looking at here, first things first, are the interactions. And to find it, you come to this classic output window. This classic output window records everything you've done in this command line format. And over to the left here, we can navigate to our current TreeNet model, and the TreeNet interactions link is at the bottom. So when I click this, we see the interactions report. The first table we get are whole variable interactions. This is a list of each predictor in the model, as well as an arbitrary score for interaction strength. So I don't have time to go over the theory behind this score, but what you should know is you can point out pretty quickly which variables are having a slightly higher interaction score than the others. And right here we can see that cement and age stand out. Sometimes you'll see a much more significant discrepancy here. Additionally, we have 2A interaction stats here. So the first one here, cement, we can see with age, cement has a pretty high score. Now these scores are two different measures on interactions based on how much they're explaining within the entire model versus how much they're explaining just within that interaction. So what do you do with this information? I might decide to only let age and cement interact to reduce the complexity of my model. Let everything else be additive. And you can do that again through that TreeNet Interactions tab. So I won't do that right now. I just wanted to point out this is a quick way to see where your interactions are and how you might want to handle them. Okay, so the next step I'm going to take is to create plots. We saw this last week, and I'll be explaining in the slides exactly how these plots are created. So I'll click the Create Plots. I'm only going to create 2D plots, and I'll select all of the important variables. We see a plot selection window with all of our plots, and when I click Show All, these are a little different than Mars. These aren't basis functions you're seeing. Instead, you're seeing for each individual variable how it's contributing to the response. So for example, on how to interpret these plots for age, you can see from age 0 to about age 100, there's an increase in contribution. And that increase looks to be about from -10 to about +15. And so you can see this as a 25 unit increase in Y as you go from X0 to X100. So these plots are averaged and centered, so you can't directly interpret this Y-axis. You have to look at it as change in Y and change in X. So what these plots do is they show you the nonlinearities present in your predictors. What I'll be showing you is how to overlay spline approximations to these plots so you can use those approximations as new transformed predictors. This is an extremely powerful tool because you can then use those transformed predictors back in a traditional regression setting. And we have seen several financial and banking companies use this method because they have regulators where the regulators say you have to use regression or you have to use logistic regression, but the users see that these TreeNet plots are extremely powerful in capturing the nonlinearity. So you're able to use TreeNet to find these transformations and put them back into regression to make the regulators happy or to make it easier for you to explain to clients or coworkers. So to do this, I'll come down to the bottom here under Smooths and click Specify. So there are several different approximations that you can set up. There's logistic, inverse, exponent, logarithm, polynomial. What I'll use here are just basic splines. So when I click this, I have to set the number of knots. I'll click 5 here. And when I click OK, this will set up 5 knot splines over every single one of these predictors. Now you have the ability to open up the predictors individually and set it up yourself based on the individual predictor. So for the sake of time, I'll just be overlaying the same thing, 5 knot splines here. When I clicked OK, you can see there is now a green smooth placed over each of these blue line graphs. Now I can double click these plots to open them individually. You can see the original plot was pretty bumpy, and now we have this nice smooth green line to explain what's happening in this variable. And you have the option here, you can move these knots around. So if you open this up and you decide you don't like how the smooth has been fit, you can change them yourself. Now that I've created the spline approximations, I'll come back down to the smooth section and click Code. Now this gives me the code for all of some predictors you may be able to use 2 knot splines, 3 knot splines, and so this will be much less complex. You can view it in SPM Basic, which is our built-in language, or in SAS code. Now for what we're doing, I need to view in BASIC so we can submit and save these spline variables. Now what this will do is that we'll save a new data set with our new variables. Submit and save, it wants me to save the data set, so it automatically gives it this name, concrete_APPR for approximations. So I'll click Save. And what happened is the engine submitted these new variables. Okay, so now that we have our new variables, I can open up that data set. Now we are approximating it. Same number of records, but now you can see our variables are the original predictors, except we've now appended _s for splines at the end. So these are now your transformed predictors. This process also created a case ID variable and a CV bin variable. And the CV bin variable just holds a number for which CV fold, cross-validation, that record fell in. So this is still just normal data. If you look at the data, now just have transformed variables. And what we want to do is we want to use these new transformed variables in regression to see if we can improve on that 66% R squared that we were getting in a standard OLS. Model setup, and I'll change the analysis engine to regression. Again, this is standard ordinary least squares regression that we're running. I need to reselect the variables since we opened a new data set. So strength is our is our target variable, and the remaining are predictors. Just have to make sure to uncheck case ID and CV bin. Now for a testing sample, as I mentioned last week, it's common practice to use all of your learning data in a standard regression model. So we'll say no independent testing, just to stay true to the original method. But as with all of our engines, you can select another testing sample if you'd like. I'm going to click Start. We run a quick, and we can see that our mean squared error is 43.59. Now, if you recall from last week, our mean squared error in a standard regression was 107, and our R squared was around 66%. We're now getting around 84%. So as you can see, we greatly improved the accuracy here just by incorporating the nonlinearities from those transformed predictors that we got from those TreeNet plots. So while you might not be completely sold on the gradient boosting, you can still use the insights and output from the gradient boosting to improve on your standard regression. And this also works the same for our logistic regression. We're still getting a regression model here with coefficients for each of your transformed variables. Okay, so I'll go back to the slides now and talk about what I just showed you, and then we'll see what we have time for after. So I showed you TreeNet's interaction control language. TreeNet models are always additive in trees, but the interactions enter at the individual tree level, and it depends on how big your trees are growing. Larger trees allow for more opportunity. Two-node trees force additive models. So the degree of interactions directly relates to the number of levels in the tree. So bigger trees, you'll have a more complex model. As I showed you, TreeNet can generate a special report with estimates of the interactions in the model, gives you a quick idea of what you should be looking for, and it also offers the additional model building flexibility by allowing the direct control over which variables are allowed to interact. And so that was what I showed you on the tab, whether you say all variables interact or only certain variables interact at a certain degree. So it's an extremely useful feature to be able to control what's interacting if you want to have a better control over your trade-off between simplicity and accuracy. Okay, so next we looked at partial dependency plots. Now I did have a few questions about exactly how these plots are created and what they mean. It's a little bit complicated, as you might see from this picture, but what's really important to understand here is that this is a post-model simulation. So once you have your TreeNet model, you're looking at how the response of your model changes while you're changing the predictors. So you're not looking at, the plots aren't showing you what's happening in the data. The plots are showing you what's happening in the model. So if you get a poor model, you'll also be getting poor plots. So what happens here is you start by fixing all of the predictors except the one that you'd like to create a plot for. So let's just say we're creating a plot for x1. So what we do is we look in our data and we fix the remaining predictors to one of the values jointly occurring in the data. So those are now fixed. The next step is to vary x1 over the range of its values. So when we do this through our TreeNet model, we're getting a response. We're getting a curve. So we're just getting one curve from doing this process once. Next, we go back to our data, we pick another record to fix the values, do the same thing to get another curve. And so you can do this for every record in your data to get a family of curves. And the way we produce the plot is we just average and center these curves. So this procedure effectively minimizes correlated inputs and is showing you exactly what happens when X enters additively. And this is the same process for the 3D plots. You would just be varying X1 and X2 values and fixing the rest. So again, this is a post-model simulation, and it just gives you insights about how your predictors are contributing in your model. Now, the more important feature that I talked about were the spline approximations. And I think this would be the most useful for those of you who are a little reluctant to give up ordinary least squares regression and who want to use these spline approximations to find transform predictors to go back into your standard regression or your standard logistic regression. This is just a picture of the window that happens when you open each of your variables individually. There are many different options. I just specified a 5-knot spline, but you have the option to pick your own knots, move them around, enforce monotone, and trim the plot ranges. Okay, the last topic I wanted to touch on today is model automation. Now this is what I think is a hidden gem of our data mining process that can really speed up and optimize your analysis with very little effort. So I mentioned earlier that we had an automation for rerunning your Mars model with different interaction settings. So we rerun a Mars model as additive with two-way interactions, with three-way interactions, and so on. Additionally, we have an automation that will cycle through different regression loss functions in the TreeNet model. After I go over this slide, I'll just pop back to the software and show you where you can find this if this is something that interests you. We have many different types of automations here. You can vary the engine parameters if you're not sure which one you'd like to use. You can do variable binning, outlier detection, different sampling strategies, and variable selection. One of the more important ones I use all the time is variable selection. We call this variable shaving. And I have described that at the bottom here. If you have a large predictor pool, or even if you have a small predictor pool that you'd like to make even smaller, the shaving can automate the process for you extremely easily and efficiently. So we have a couple different options. You can shave variables from the top. So that means eliminating the most important variable each time, rebuilding the model, and seeing how the performance changes. You do the same thing from the bottom of the importance list, and this is a good way to drastically reduce the number of variables. If you have hundreds of variables that are sitting at the bottom of your model, kind of contributing a little bit, might not be that important, it might be better just to get rid of them. And then finally, there's shaving by error, which just tries to get rid of the variable that's contributing the least. Now this can be useful. Sometimes what I do is I'll set up a model run at the end of the day to shave the variables. And when I come back the next day, I have a nice automation summary of different models with varying complexities, different predictor pools, and I can choose by looking at them side to side to see which one's giving me best accuracy, which one has the smallest number of predictors, etc. So now that I've explained this model automation, I'll just show you quickly. In Model Setup, this Automate tab. There's many different chances for automation here. And when you click them, they'll let you know what they are. So what I explained for TreeNet regression is this will just rerun your model with a different regression loss function. Then you can see them back to back. I'll show you quickly how to do the shaving variable, shaving automation, to see which of your variables might drop off. I'll do it from the bottom of our predictor list. This just gives you an idea of how quickly it works and the type of output that you'll see from it. So you can see here we're building 8 different automation models. Each one is 500 trees, and at each model it drops off one predictor. Now this might be something you do manually. This can speed up that process, but if you have hundreds of thousands of predictors, this can be extremely useful. And so what we get at the end of this is a nice automate results window that gives you a graph against your model quality choice. Here it's mean squared error. You can also switch to squared. And it lets you know which variable was shaved off and how the performance suffered or improved. You can open them up individually as well. So this is just a quick overview of the different automations that you can perform here to speed up your process. Once you've found the model that you liked or found a model that you think performs pretty well, you can start using these automations to refine that model even further. So the last thing to touch on today are the other applications that you can use these regression techniques for. Obviously, I showed you a civil engineering application today, but there are many others, and some of these are based on the request that I got from last week. So these techniques are being used in dental research. Here's one example, predicting risk of obesity and type 2 diabetes in children using saliva samples. And this is from Dr. Max Goodson at the Forsyth Institute. And he's doing great research with these methods, and we're actually hoping to feature him on one of our podcasts soon. So stay in touch with us to get information on those podcasts and possibly hear Max Goodson in the future. We also have economics papers, ecology, and business, and these are all linked here so that once you get the slides in the follow-up email, you can check them out yourself. You can also check out the other ones that we have on our website. More applications in epidemiology, looking at the relationship between vitamin E levels and myocardial infarction. We also have healthcare, numerous social sciences applications. If what you're looking for you don't see here, please contact us, check out our website. We can help you out in showing you how these methods and these regression techniques can be used in your industry. Okay, so we'll move on to talking about questions now. We have a few minutes to go over a few of them. If you happen to think of any more after the webinar, please email us at support@salford-systems.com. You'll be receiving the follow-up email either later today or tomorrow with a recording of the webinar so you can review the PowerPoint slides I showed you today, the trial download instructions for our software, and a tutorial with the data set so you can replicate the exact steps I showed you today. Again, if I can't get to all the questions, which I'm sure I won't be able to, last week we got over 60 questions, so it took me a little while to answer, so I'll try and get them back to you today. If not today, you'll definitely get an answer tomorrow. Okay, so I'm looking at some of the questions here. One of the questions is there a way to generate code/syntax from the selections you make in the dialog boxes so you don't have to point and click your way through an iterative or repetitive analysis, or so you can experiment with parameters? The answer is yes. Every selection or click that you make in the dialog boxes is recorded. So I'll show you back in the software. As I mentioned, this classic output window here records everything you. Additionally, we also have a command log. So there's a shortcut here to view the command log. And this opens up that you built. So for example, we modeled strength. We also ran an automate shaving. We can see this keep statement lets us know which variables we kept in our model. So this gets recorded for every move you make. Then you can save this command log, you can open it up, and you can click File Submit window next time you're in to rerun exactly what you did before. Or as you mentioned, if you want to experiment with parameters, do your own types of automation, you can easily save these command log files or create your own command files to do just that. So you don't have to do all this repetitive point and click work. Okay, next question. We have a question on how to write our final regression equation using Mars. So the final equation in Mars is what I showed you in that basis functions tab of the model. You'll have each of your basis functions established, and then your final model, y equals intercept, plus your coefficients and those basis functions. So it's very similar to a standard linear regression equation, except you have to establish those basis functions first. We have a few questions on getting a copy of the slides for Part 1 and Part 2. So for Part 1, we do have a separate registration link on our website. When you sign up for the Part 1, you'll see the recording of last week's webinar as well as the slides and the other materials I mentioned. For Part 2, you'll be receiving that follow-up email sometime today or tomorrow with a copy of the slides. We have some questions on applications and property and casualty insurance. I'll be following up with you after the webinar, and I'll send you what we have for that. Another question is, can you produce code for R? Currently, this is not one of the languages we translate to. Let me switch to the software here, and I'll show you how you can translate the model. So here we have our TreeNet. We have a translate button in the bottom right corner. In SAS, C, PMML, and Java. You can save it as a separate output file, or it will print straight to the classic output window in any of those 4 languages. Another question of can we produce code in Python? Again, as I just explained, we're currently supporting translation to SAS, C, Java, and PMML. Okay, so some of the other questions here are a little bit more complicated, and I'll be answering them offline just so I can give you a better explanation, and I can also provide some resources for you to better answer them. So thank you everyone for joining us today. Go ahead and register for Part 1 from last week if you'd like to review that as well. You'll be getting a follow-up email later today, and hopefully all of your support questions answered by the end of today as well. Thanks for joining us, and I hope you all have a great day.